back. All right, so Taylor series, something that's not actually taught at school, but probably should be and probably will be in about 10 years' time. So you were talking about functions before and how there's, they can be a bit confusing. There's lots of different kinds of functions. When you study GCSE maths, a lot of the functions you study are called polynomial functions, where they can be written like, let's see, a0 plus a1 to the x plus a2 x squared plus a3 x cubed, and so on, all the way up to, I guess, x to the infinity. And this is general, they're called general polynomial equations, and the order is the highest power that's in the polynomial. And this guy called Taylor was thinking like, well, what if like other functions like maybe the sine function or the log function can also be expressed as a polynomial. So this isn't a trick for polynomial functions because we already can write those as polynomials. This is a trick for trying to write other kinds of functions as polynomials. So I'm just going to assume that a function exists and it can be written this way, and that's it. So I can also write this using the summation notation and say that it's a bunch of constants times x to the power n, and n goes from 0 to infinity. Is that okay so far?
Mm-hmm.
Okay. Right. Okay, so in order to understand this polynomial, really what I need are these constants. I need to understand what these constants are. So how can I find the constants? Any ideas?
I mean, there are no numbers, so I'm not sure right now.
Yeah, exactly. It's a little bit strange, but what I can do is this. I can set x equal to 0. Okay, and I can evaluate f of 0. So this is actually, in my opinion, a very strong argument for saying that 0 to the power of 0 is 1. Because I could have written this with an x to the 0 here. Yeah. And in fact, if you look at this sum, it would have. So what I'm saying is, ignore the fact that this is here and then set x to 0. All of these terms will disappear, except for the first term, because 0 to the power of 0, I'm saying, is 1. There's a lot of debate about that, but basically this is just some evidence that it could be 1. Let's just assume it is 1. So when I set x to 0, I get f of 0 is just a0, right? I just get the first constant back. So whatever the function is, if I know how to evaluate the function at 0, I can pick off that first constant. So let's just imagine the function is the sine function. Sine of 0 is 0. So my first constant would be 0. Okay. All right. What about the other constants? How do I find those? Any ideas? How could I get rid of this x?
Make it a 1.
Make it a 1. So set x to 1. It's not a bad idea. I would get all of the constants if I set x to 1. I want to try and pick them off one at a time. That should be a plus there, should be. Any other ideas? How could we get rid of x to the power 1?
Make it a 0.
Yeah, okay. So the answer is we differentiate. Okay, we differentiate f of x, and then we evaluate at 0. So first I have to I should probably differentiate. So let's just do the differential. So f dash of x is this is Newton's notation for df dx. What happens to the first term when I differentiate?
It becomes 0.
Yep, 0. Okay. What about second term?
1.
A1.
No. You.
Well, you bring the 1 down, right? From the
Just
power.
A1.
So you bring the 1 down from the power. So you have 1 times A1.
Just X.
The x will disappear, go to 0. So you just get A1.
Oh, right. Okay. Yeah.
Okay. And then the next one, what will we get? We'll get 2 comes down, A2.
A2X.
X. And then what? 3 comes down, A3, x squared.
Yeah.
And so on. Okay. Then we set x to 0 again, and we evaluate the derivative of the function at 0. So what this is essentially doing is it's like, say there's a function, it could be doing anything. Then if I evaluate the function at 0 and I pick off that constant, I picked off the y-intercept. Then if I differentiate the function and set x to 0, I'm picking off the slope, and I'm making sure that the slope is the same at x equals 0. And then as we're going to do for higher and higher derivatives, essentially what we're doing is we're fixing all of the higher derivatives to be the same as the function at x equals 0. And we're generating, building up the function from polynomials terms piece by piece, essentially. So f dash of 0 then, well, when x goes to 0, this term and all of the higher terms are going to be 0 because they contain an x. So we'll just get a 1. Okay. All right. I just need to do a couple more of these. You'll see why. So f double dash of x means differentiate twice. So that's going to be differentiate once. I've got up here. So differentiate twice. I'll just differentiate that one. The constant a1 goes to 0, right? Just a constant, no x term. 2a2x goes to 2a2. Okay. What about the third term? What happens to that when I differentiate?
6a3.
What happens to the x squared? This is all constant, right? 3a. So that stays the same. I'm going to have 3. I'm going to have a3. What happens to the x squared when you differentiate?
Don't you?
Isn't it differentiate 2 times already? Wait.
2x, yeah.
Or it's just become.
Okay.
So yeah, isn't it 6?
Yeah, 3 times 2. I'm going to write it as 3 times 2 because I'm going to hope you'll spot what happens in general if I write it that way. So I'll still have an x to the power 1. My next term, if I write it in, it would have been 4a4x to the 3. So now if I differentiate that,
12.
yeah, 4 times 3 times a4x to the 2, and all of the higher order terms. Okay, then I set that to 0. And I basically get rid of all of the terms that contain an x. Okay, and I'm left with 2a2. Okay. So differentiating 3 times, then this is also written as 3 in a bracket. So this is different from f cubed of x. If it has a parenthesis or a bracket there, it means differentiate. So this is differentiate the function 3 times. So if this is differentiating twice, then I just differentiate that. So obviously the constant at start goes to 0. Don't need it.
Mr.
3
David.
times 2. I'll keep it written as 3 times 2, a3. Okay, what do I get with the next term? 4 times 3, the 2 comes down. Okay, 4x. Okay, can you see what's happening here in front of these terms? What do you call that? 4 times 3 times 2.
Factorial.
Yeah.
Brilliant. Yeah, 4 factorial, right? So I can replace this with 3 factorial and this with 4 factorial. And in general, now, if I was to differentiate n times, I would end up with n factorial an. Okay. So my an, I can rewrite as the function differentiated n times and then evaluated at 0 divided by n factorial. Okay. So let's now use this powerful trick. We can rewrite our function, and instead of having the constants times the x values, I can now rewrite it using this for the constants, and you'll see why that becomes useful. So my function f of x can be thought of as a sum from n is 0 to infinity, and then it would be the constants, but the constants are just found by differentiating the function n times, evaluating at 0, divided by n factorial, and then that will be multiplied by x to the power n. Okay. So this is the powerful formula. I could have started here, but I think it's quite easy to actually derive this thing. And you only need to know how to differentiate polynomials, which you know how to do. So let's try cosine. Let's think about cosine of x. Let's say f of x is cosine x. And I'm saying that that can be written as this infinite sum of terms, polynomial terms. Okay. So if I want to find the first term, that's going to be when n is 0. Okay, so when n is 0, I don't differentiate the function at all. When n is 1, I differentiate once. When n is 2, I differentiate twice. So f brackets of 0 means don't differentiate and then evaluate at 0. So cosine of 0.
1. Wait.
Good. Cosine of 0 is 1.
Okay.
0 factorial is
1.
good.
Wait, 0 factorial. Yeah. 1.
It is 1. So this is 1 divided by 1. X to the power of 0 is
1.
So everything's 1. Okay, that's my first term. Second term, differentiate. So that's my first term is when n is 0. My second term is when n is 1. So differentiate one time. What's the differential of cosine?
The not cosec. Wait, no, this is
Okay, what's the differential of sine?
cosec.
Yeah. So if I differentiate sine, I get cosine. What happens if I differentiate cosine?
The other one does not call cosec. Wait.
I get negative sine.
Oh.
And then if I differentiate negative sine, I get negative cosine, right?
Yeah, forgot.
And then if I
already.
differentiate negative cosine, I get sine. So you differentiate sine, you get cos. Differentiate cos, you get minus sine. Differentiate again, you get minus cosine. Differentiate again, you go back to sine. Okay. You should probably know those for pure. You don't need them for stats, but you will need them for pure. So when I differentiate cosine, I get minus sine. Minus sine of 0 is going to be 0. Okay, so my second term will just be 0 because sine, and actually all of the odd powered terms will be 0 because they'll all contain a sine. Okay, does that make sense? Okay. So what this means is don't differentiate the function, evaluate the function at 0, divide by n factorial times by x to the n. So when n is 0, it's all 0, n is 0 for all the terms. Okay, plus the next term, differentiate once, divide by 1 factorial, evaluate 0, x to 1, plus the next one, okay, plus the next one, and so on and so on. So what I'm saying is for the first term, when n is 0, we don't differentiate. So we just get cosine of x. We evaluate that as 0. Cosine of 0 is 1. X to 0 is 1. 0 factorial is 1. So everything's 1. The second term, we differentiate cosine of x to get sine. Sorry, differentiate to get minus sine. Minus sine of 0 is 0. So this term goes to 0. Okay, next term. Differentiate twice, we're going to get minus cosine. Okay, cosine of 0 is 1. We're going to have an x squared, and we're going to have a 2 factorial. Okay. All right. Next term. We're going to differentiate 3 times. So we'll start with cosine, differentiate minus sine, differentiate minus cosine, differentiate sine. But sine of 0 is 0. So again, this will be plus sine of 0 over 3 factorial x cubed, but that will be 0. Okay. And every term that contains a sine will be 0. Yeah?
Yeah.
Okay. Because the sine of 0 is always going to be 0, right? But the cosine of 0 is always going to be 1. So this is when n is 0, this is when n is 1, this is when n is 2, this is when n is 3. So for the odd powers of n, or for the odd values of n, I should say, you'll always get 0. For the even powers of n, or for the even values of n, I will get 1 coming from f to the power, f differentiated n times, I'll just get 1 over n factorial. Okay, so I can already write down what the next term is going to be, right? It's an even power, so it's going to be 1 over, and it's the 4th term, so 4 factorial x to the 4. Okay, and then I just have to decide, is it positive or negative? So I started with cosine, differentiate to minus sine, differentiate to minus cosine, then it's sine, then it's cosine, so it's positive. Okay. The next term will be a 0 again, because it will contain a sine, and then I'll be back to minus cosine, so then it will be minus x to the 6 over 6 factorial. Okay, and if I just write this out and ignore the 0 terms, then you can kind of see 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6. You can see it oscillates between positive and negative, but it's only even powers. Okay, so that is another way to write the cosine function. I'm just going to take the first 2 terms as an approximation and just put them into Desmos just to show you that that actually works. So what was it? Cosine of x. Okay, and I'm saying is equal to 1, was it x squared over 2? Okay, I think it was minus, wasn't it, for the first term? So there you go. You can see that my function with the first two terms is quite a good approximation for cosine around the input of 0. And actually Taylor did this in general. You can just change x to x minus a, right? And I can just change this x to x minus a as well. And I can then shift the function by a. And you can see it will approximate it wherever a is, right? So, you know, there's nothing special about 0. This will work wherever you want to approximate the function. Okay, let's just get rid of that. Don't need it anymore. Cosine x.
I kind of get what you mean, but I'm
Yeah.
trying to like get
Exactly.
it into my head because this is a lot.
It is a lot, and you don't need to worry about the shifting by the a. That's a bonus. So the next term will be x squared of x to the 4 over 4 factorial. So let's add that one in. X to the 4 over 4 factorial. Got to be careful with the notation there. There you go. So you can see now it's a better approximation. And the more terms I add, if I added all of the terms, it would be exactly the function. And you can do this yourself if you want. You can play around with it just by adding more and more terms. You can see how it better approximates the function. And this is called the radius of convergence, is like the region where it is a good approximation. So the more terms you add, the bigger the radius of convergence, and the better you can approximate the function. So that is that's cosine, is all of the even powers with an oscillating sign, so the sign changes, divided by the even power factorial. Okay, so what do you think sine would be? Sine of x. Probably should have started with that one, to be honest, but any ideas?
The opposite of cosine, like the even will not have number and the odd will have number.
Yeah, and that's basically exactly right. You have the odd powers. So we started 0 as an even number as well. That's seems to be apparent from this. So let's say 1 is the first odd number. So we'll have
So, Mr. David, you're just applying these to actual values, right? But these can be used in any situation, basically.
yeah.
That it's not that aren't general polynomials.
You wouldn't need to do it for a polynomial function because it's already written as a polynomial.
So basically everything other than polynomials.
Yeah.
You can use this for, but these are just examples, right? It's not just specific to these.
Yeah, exactly. It's not just specific to the trig function. That's what makes this so powerful. And actually, like these first two terms here, physicists use this as an approximation all the time for cosine. And the same for sine, they'll use the first two terms because it's so hard to work with those functions. It's much easier to work with polynomials. And so if the angle is small in a problem and there's not much variation in the angle, then it doesn't matter. The approximation is almost just as good as the function, so you can use it. So sine is going to be all of the odd powers. Oh, by the way, we could write this in summation form. Say this is the sum from n is 0 to infinity. This time it's going to be, let's see, it's -1 to the n. x to the power 2n. Okay, the 2n just picks out even powers. X to the power 2n over 2n factorial. Okay, and then we need every minus 1.
Mr. David,
Yeah,
are you writing right now?
yeah.
I can't see anything. Oh,
Okay.
wait, okay, it's just
I
really,
can just, yeah, I'll just go down. I'll go back to here. That's all right.
it just became gray, so it's really like,
Maybe
really
can I
right now.
make it any thicker?
So if I ask you a question like, what is the main function of governance? Okay, what is governance?
Sorry about that. I don't know what's happened. That's maybe a little bit better. So let's just do sine. Okay, so my formula was differentiate the function n times evaluate at 0 n factorial x to the n. So don't differentiate sine. You're going to get 0 for the first term, right? Because when you plug in 0 to sine, you get 0. Okay, when I differentiate sine one time, I get cosine. Cosine of 0 is 1. So I get x over 1 factorial. Don't really nice to swear that. Next term will be 0 again. Next term will be an odd power again. But this time it will be negative because I've differentiated minus sine to get minus cosine. Minus cosine of 0 is minus 1. And this is the fourth term, so it'll be the third term. 0, 1, 2, 3. So n is 3. Fourth term, but n is 3. So x to the 3 over 3 factorial. Okay. And we keep going. We'll have plus x to 5 over 5 factorial minus x to 7 over 7 factorial plus blah, blah, blah. Okay, so you can see that sine of x is just the odd powered terms. So we've got x minus x cubed over 3 factorial. Odd powered terms divided by the odd numbers factorial. And again, with a changing plus and minus sign. Okay. So now it's sort of easy to spot what happens if you was to differentiate that polynomial. What happens when you differentiate the first term x? You just get 1 minus 3x squared over 3 factorial. The 3's will cancel and you just get minus x squared over 2 factorial. Plus x to the 5. Well, you'll bring the 5 down, so that'll become x to the 4, and the 5 will cancel with the 5 factorials, so leave you 4 factorial. So it becomes obvious that when you differentiate sine, you get cosine.
Wait, Mr. David, so the point of changing these into polynomials would be to, like, why would you need to change these into polynomials? Like, how would that help you?
Okay, just let me do a couple more. How long do we have?
We have
13 minutes.
13 minutes.
13 minutes. Right, let's do E then. Okay.
So I mean, I get what you're doing and how you're doing it. Just like, when would I have to use these? Like,
well, let's say that there was some piece of data that was approximated by one of these functions, and let's say you needed to integrate it or something, and it was actually this is a really good one to think about, the exponential function. Like, what is e to the power of 3? Think of that as like e times e times e, right? What about e to the power of 3.7? how would you work that out? How does the calculator work that out? So we need another way to think about these functions, and that's exactly how the calculator works it out. It uses the Taylor series expansion as a polynomial, plugs in 3.7.
Okay, yeah.
You can also do it with, if you get to the stage of complex numbers, you can do it with complex numbers as well. So let's think about the exponential function. It's a really nice, simple function to differentiate. So the exponential function of x, and again, I'll just write down the formula. So it's f differentiated n times over n factorial x to the n. So don't differentiate e, evaluate it at 0, e to the 0 is 1, 0 factorial is 1, x to the 0 is 1. So the first term is 1. Okay, that's for n is 0, because we're starting from n is 0. N is 1, then we differentiate e one time, we just get e to the x. Evaluate at 0, we're going to get 1. This time will be over 1 factorial x to the power 1, right? Okay, plus the next term, n is 2, differentiate e twice, but you're just going to get back e. Evaluate at 0, you're going to get 1 every time. So we're just going to end up with x to the n over n factorial. So e is just x to the n over n factorial. But as a sum, from n is 0 to infinity, is the exponential function. And now you could plug in 3.7, right?
Oh, okay. Yeah.
What is, if let's say we have a discrete random variable now x, that it follows a Poisson distribution with parameter lambda, then the probability that x is equal to r is given by what formula?
I forgot.
Okay, it's given by lambda to the r, let's say, over r factorial e to the minus lambda. What does the lambda to the r over r factorial remind you of?
The f power n.
This part looks suspiciously like this part, right?
Yeah.
Okay, what's missing though? What's not there?
The sum.
Yeah, the sum. So this isn't adding up all of the terms. This is just picking out one of those terms. Okay. If I was interested in the probability of x being less than or equal to r, then it would include a sum from n is 0 up to r, lambda to the power n over n factorial. I'd have to use this type. And then that would need to be multiplied by e to the minus lambda separately. The e to the minus lambda is just going to be a constant. The exponential e as a number is just a constant. To the power of something that's also a constant, right? The lambda is just the rate, it's the mean. So these two things here, that's just a number. Okay. E is a positive number. Lambda is a positive number. When you have a number to a negative power, like a to the minus n, it's 1 over a to the n. So it's 1 over e to the lambda. It's 1 over positive number to the positive power. It's a positive number, but it's a small number. Okay. If this instead didn't stop at r, but went all the way up to infinity, then this part here would go to e to the lambda. Okay, because this is e to the x, right? The input here is x, and I've got an x in here to the n. So if my input in here is lambda, then it's the input of the function. So this is e to the lambda times e to the minus lambda, which is 1. And that's when I'm counting all of the terms, every single term. But if I'm not counting all of the terms, I'm just counting one specific term, then this is not e to the lambda, but it's lambda to the power n over n factorial for some particular n. Okay.
So
Oh.
Okay.
So back to Desmos. Let's see. That's L for lambda. Let's make a function. F. Have I got time for this actually? Just about. F equals L to the power of, let's say, n over n factorial. Okay, all right, I'll just take off those two. You don't need to see them. So this is like the first part of the first part of the Poisson distribution. And then this gets multiplied, it gets scaled by e to the minus lambda. So that's going to be e to the power of minus L. As you can see, that just gives me a constant. I'm going to have to make this a function so that Desmos will let me do something. Okay. So now I've got my, as you can see, when lambda increases, the function g, which is e to the minus lambda, gets smaller, right? But when that number is less than 1, you can kind of see that e to the minus lambda gets bigger. The other purple function, which is just L to the n over n factorial, just gets bigger as lambda gets bigger. And it makes no sense, like what's happening over here, just ignore that. This function only really works like when you can plug in a positive rate for lambda. Okay, now let's just compose these two functions. Let's say h.
Mr. David, there's somebody here.
Yeah, maybe they're a little bit early. H equals fg, g of x. Okay, so this function h now, that is basically the Poisson distribution. And I can even show you that by typing it in: distributions, Poisson distribution. And what's my lambda at the moment? 1.3. There you go. The blue function matches exactly with the Poisson distribution. Okay. So you've got the first part of the Poisson distribution, which is like the rate to the power n over n factorial, and that part, you can see it kind of like grows, this purple part, as the rate gets bigger and bigger, but it gets scaled by this other part, the red part here. And the red part scales it back down and essentially normalizes it so the probabilities are all normalized. If you think about what the Poisson distribution is telling us, this is like, let's say L is 2.2 right now. It could be, there's an average of 2.2 cars that go past my window every minute. What's the probability I only see one car go past? 0.35, well, sorry, let me change the rate in here. What's the probability I only see one car go past with average of 2.2? It will be 0.244. What's the probability of seeing two cars go past? 0.268. Three cars, 0.197. So this is the Poisson distribution. So to really understand what the Poisson distribution is, you need to understand the exponential function and the Taylor series expansion of the exponential function. When I add up all of the probabilities, I'm adding all of them up, then of course I'm going to get 1, which is what happens when I have e to the lambda times e to the negative lambda. Okay. So in general, we have x is distributed with a Poisson distribution with a mean rate. we can ask what's the probability given some lambda that I observe X to be R, where R is just a number. It could be 0, 1, 2, 3, 4. All right. So when you're plugging it in here, you're only plugging in one number for R. So let's say I was interested in the probability of it being 3, the probability that X is equal to 3. I would do lambda to the power 3 over 3 factorial e to the minus lambda. Okay. If it's the probability that X is less than or equal to 3, then I would need to do the probability that X is 0, 1, 2, and 3 and add them all together. Then it starts to resemble that sum. Okay, and if I add them all together, so X is less than or equal to infinity, I'm adding all of them together. I'm getting lambda to the n over n factorial added up infinitely many. That's just going to be e to the lambda. So in the limit as n tends to infinity, this tends to e to the lambda, and then that would tend to 1. So that's just basically saying that the probability for all of them will add up to 1. But if you pick out individual ones, then they'll have a finite probability between 0 and 1, according to the formula. Okay. All right, that's a lot of information.
Yeah.
So I'm going to leave it there, stop recording.